Good afternoon. We are now joined by Duan, who is the Program Director at the Division of Health Informatics Technologies at NIH, Dr. Rafael, who is the Lead Artificial Intelligence Tech Sprints Coordinator at Veterans Affairs, Dr. Amy Justice, who is both a Professor of Public Health at Yale University and a long-serving physician and research director within the Veterans Health Administration, and by David Womble, who is the Artificial Intelligence Program Director at the Department of Energy's Oak Ridge National Lab. David, Dr. Justice, Dr. thank you so much for joining us. So I want to start out with an opening question for Dr. Justice. And Dr. Justice, it looks like over your time at VA, you have helped oversee and direct some of the agency's most substantial public health research programs, looking into conditions ranging from HIV to COVID-19. And from my understanding, these programs require a pretty significant input of information from various sources, especially a heavy reliance on health informatics to really refine your research and analysis. And I'm wondering, in light of the investments that VA has made in capacities ranging from EHR to data interoperability, how have these been used to help support your research endeavors over the past, 3-4 years?
Well, it's really a 20-year story rather than 3 or 4 years. The VA is at least a decade ahead of most other health systems in terms of having a paperless medical record on our veterans. That started back in about 1998 to 2002, where it became very complete and truly paperless. That record was established at all the VA facilities, so over 120 medical centers across the country. And because of that, we've had a long time to learn how to use this data, how to bring it together, how to make sense out of it, how to clean it, which is not a trivial problem, and how to standardize interpretation of it. And I can't underemphasize how important those pieces are. And whether you call that informatics or basic clinical epidemiology, it's really the same issue. Once you get the data, the work begins. It's not like having the data solves the problem. You have to have the data, but you also have to be able to make sense of it clinically. And that requires close collaboration between clinical experts who understand how that data has been recorded and people with both epidemiology and informatics expertise to try to really make it sing in terms of answering the questions that the clinicians most need to have answered.
Absolutely. And I want to ask a question about one of the more recent research programs you've looked into, because if memory serves, VA released a pretty landmark study on risk factors around ethnicity, race, and COVID-19 in October 2020, which was barely 6 months over when the pandemic was announced. So I'm kind of curious that in light of that, how are these, again, these investments you've discussed that have been really momentous over the past 10 years, how did that really help refine and maybe expedite your research that went into the COVID-19 study?
Because the process of cleaning data and making sense of it takes a lot of time, the fact that we had already done that for VA electronic health record data and for other ancillary data sources that are relevant to that analysis, we could bring the data together and make sense of it quite rapidly. Further, because the VA is now storing this data in a central data repository that's updated nightly, we were able to get very recent data and do those cleaning steps with it. And combining that with AI expertise in terms of how to automate as much of that cleaning as possible, we were able to very rapidly respond.
Absolutely. I can only imagine how conducive that was to answering and helping research what was an active public health crisis, really kind of streamlining the research and helping deliver there. My next question I want to ask is for Chi, and it looks like Chi, much of your research work and that of your team at NIH has really centered on health imaging tools like MRI and ultrasounds that are really important for diagnostics. And I'm wondering, in light of that, how has the growing usage of advanced data analytics at NIH really helped refine these capacities that have, again, serious implications for assisting with patient outcomes?
Yeah, thank you for having me. Right now, I can think about 3 aspects. Firstly, in some applications, especially for those involving extracting features or finding patterns in the data, the advance in data analytics has lowered the bar to entry or shortened the development time for the first in-human prototypes. And this could potentially accelerate the technology transformation into healthcare. And secondly, it has broadened the dimensionality or spectrums of our data analysis capability, enabling a more comprehensive approach in understanding and managing diseases and conditions instead of the traditional siloed or organ-specific way. And for example, because COVID-19 affects many organ systems involved in the NIBIB pandemic response, the Medical Imaging and Data Resource Center, or MIDRIC, could enable clinical decision support tools to diagnose and monitoring the acute COVID or long COVID in some cases in a systematic way. And lastly, advanced data analytics could help us to understand and then address the gaps that were overlooked before, such as hidden biases in the algorithms or lack of diversity or representative data in some of the AI algorithms that were developed on the siloed data. And one of our data scholars at NIBIB, Dr. Judy Chicoya, has a recent publication on the critical gaps on AI development on this topic.
Absolutely. It sounds like it's really helped refine the sophistication of these capacities in a very impactful real-world way. And I want to turn back to VA for a second, because again, VA has been responsible for overseeing both COVID-19 response, but really kind of advancing America's medical understanding across fields ranging from oncology to public health. And Dr. Fricks, with your work at the National Artificial Intelligence Institute, or NIA, it looks like a lot of that rests on these really momentous forward-looking tech sprints where you bring together both VA's expertise, but also partners from academia and the private sector. And can you tell us a bit about how these tech sprints are organized, and what are some of the research questions you've really focused on answering through your AI research?
Sure, yeah. And first of all, thank you for inviting us. A bit of background on the NIA. The National Artificial Intelligence Institute was founded about 2 years ago. We've helped shape the National AI Initiative and National AI Strategy, the VA AI Strategy. I'd encourage people to go to ai.gov to learn more. But yeah, so one of the key ways that we advance AI at the VA is through running these tech sprints, which are essentially a 3-month competitive process where we invite outside teams to work with the VA. So typically, these are teams ranging from industry to academia that bring a new perspective on some problems that we might put out. And we provide some VA data, some de-identified data, or excuse me, some synthetic data, as well as weekly interactions with clinical experts or NIA experts, for instance, to develop a prototype that fits within VA needs. So this is a very productive way for us to work with industry to collaborate on new solutions, to vet new solutions. And we've had a number of pilots, I think at least half a dozen by my last count, that have been discovered through the AI Tech Sprint that are new approaches that apply AI to VA problems. So it's been a very productive program, I think, for all parties.
Absolutely. And I want to backtrack a bit to your mention of synthetic data, because it's clear that these tech sprints require a significant amount of information to, for example, test and develop models. And it sounds like not all of that can be precisely drawn, if you want, again, assuming a large diversity of data, fully drawn from, I guess, real data. So can you give us a bit of background on what synthetic data is, how it's developed, and how it plays kind of an essential role in really powering your tech sprints and your research?
So, well, first of all, the VA is the largest health system in the United States. We have a patient population of, I think, about 10 million patients. We could have billions and billions of data. So it's actually not really a limitation of the data that we have, but rather that, the VA, one of our key goals is protection of the privacy of our veterans, we're good stewards of the data. And so our de-identification standards are quite high. So typically the VA is, very precise about how we de-identify data to make it available. But on the other hand, a lot of these AI developments are really built on and refined by the availability of large volumes of data. So while we have some of this available to internal researchers, to work with external partners, that's quite challenging. So an alternative to de-identifying real medical data from patients is synthetic data. So that's any sort of process where we apply perhaps modeling techniques or different types of inference to understand the relationships between different fields of data, and then use those relational understanding, whatever model we have of perhaps the disease process in the real world, to then generate a completely artificial set of data points that is, reminiscent of the original population, but doesn't represent any particular individual. And actually, we partner with a lot of VA researchers to generate synthetic data. And the advantage of synthetic data is that it really helps us, there are significantly fewer or no privacy concerns with sharing synthetic data. And so we can often share that through the Open Data Initiative at data.va.gov. And it's an ongoing project, really. We have a lot of work in the pipelines. I'd like to point out especially the MD Clone project, or the project with MD Clone, I should mention, where we're working to refine data synthesis techniques.
Absolutely. And it sounds like making sure that those data synthesis techniques are as up to date and as advanced as possible are really essential for, as you said, data privacy and creating what is fundamentally ethical AI that is, again, respectful of these necessary parameters. And we've been talking a bit here about the uses of AI, but I want to get down to the fundamentals of what is necessary for powering AI. And this is more of a question for David. And it looks like DOE and your team at the Oak Ridge Lab has really emerged as one of the federal government's frontrunners in developing high-performance computing to support, these kind of AI projects and research. And I'm kind of curious, how have DOE's capacities really advanced over the past decade, and how has this, investment and focus on developing high-end and high-powered computing really helped support your mission at Oak Ridge?
Adam, thank you for asking me to join the panel, and thank you for the question. DOE does have a strong computing mission that really, I would have to say, can date back to the Manhattan Project and the nuclear deterrence mission that has become part of DOE. The current mission around science leading into the AI and enabling AI is something that's evolved over the past approximately 30 years as DOE has taken on the high performance computing mission around the economic security and scientific leadership for the nation. Now, of course, 30 years ago, that really meant the traditional modeling and simulation, solving large-scale equations. But as our ability to collect, store, and process data has changed or has increased, the computing capabilities have mapped into the new mission space. I think we do a lot of work to focus on developing new architectures. We work closely with industry and the computing industry partners to deliver these big machines, but we maintain several leadership class facilities that are available for open science as well as for any of the applications we've talked about here. So it's a very open machine. The cycles are allocated on a proposal basis. So we do that for the country. Now, of course, the appropriate architecture for AI is an evolving target. Right now, we still have a lot of our big machines that are focused on the accelerators that have been used for traditional modeling and simulation. While at the same time, industry has introduced a lot of new chips, a lot of new computing technologies, and we're in the process of evaluating and looking at the next generation of high performance computer that does best support AI. We are working through several procurements now in which we are going to adapt these architectures, and we'll expand not just from the big centralized computer center, but to a more of a computing ecosystem. AI has the ability to run embedded in edge devices, for example, in cars, in phones, and things like this. And so the question now becomes in the HPC computing mission, how do we integrate that into a full ecosystem? So there's a lot of research going on. We also develop a fair amount of software infrastructure needed to run these machines. And I'll emphasize that a lot of this is in partnership with industry partners. And finally, we deal with a lot of data. We have secure data enclaves. We work closely with many of the agencies here, including the VA and others, about some of the ways to manage data in a fair, accessible way while respecting the privacy needs and things like this.
Absolutely. And it sounds like there's a lot of interesting promise and, focus on potentially, as you'd mentioned, integrating edge and 5G and how those really come together. I want to get to a bit of a more foundational question. And it looks like there are a lot of institutions, both in public and private sector, that really want to engage in substantial AI and machine learning work, but they might not necessarily have their own in-house structures to support that. So I'm wondering what, in terms of, say, computer resources and energy usage and processing power, does an organization really need to have in order to support its own AI research?
There probably isn't one answer to that question. It depends very much on the application that you're going to want. If you're, for some of the science that we're doing, we can actually do quite a bit with fairly small computing, but also some of the large-scale science, the neutron science, the look at the energy infrastructure, climate infrastructure, health, biology especially requires quite a bit of computing. Now, of course, we have a big machine here, Summit, at one point the most powerful machine in the world. And so it gives us a resource that we actually, as I said, make available to the world, but it gives us the ability to compute some of these large models and on very, very large data sets. Google, Amazon, many other companies make their resources available commercially. And so companies do have access to those as well. Computing is critical to AI. So even though there are things that can be run, small models, small data, to a large extent, this has become a really major consumption of power in the country. So that does open up a whole new research area about the most efficient way to compute AI. How can I compute with less data? How can I compute with smaller models? How can I train more efficiently? Fewer epochs, fewer passes through the data in order to get a workable model. And then how do I characterize that model to give the user confidence in that? That's an active area of research to reduce computing actually needed. And but we have a long way to go yet.
Yeah, and that's really interesting. And you mentioned energy efficiency. I'm going to go out on a limb here and imagine that there are a few parts of the government that have a greater focus and expertise on energy efficiency than DOE. So I want to bring this next question to Chi. And Chi, it looks like a lot of what work is being done at NIH in terms of kind of applying these capacities focuses on your mission towards advancing, say, certain kinds of, for example, diagnostic tools and medical tools as well. And I'd guess that there's potentially a lot of work with other areas of the government to kind of bring these up to speed and approval so they can be adopted more widely into public use. And I'm wondering, how has NIH worked with FDA to really codify standards around the usage of data analytics and imaging capacities for healthcare? And how have you really helped these being more adopted on a wider scale?
Yeah, thank you for the question. FDA, as we know, is the regulator of medical devices, and they have been working with consensus standards for decades in order to improve the safety and effectiveness of the medical device. NIH, on the other hand, is traditionally investing in technological development, including some of the work may translate into standard. One example is that one of our national centers has been co-leading the efforts in developing standards for prostate imaging reporting and data system, or PIRATS, which could help to improve early diagnosis and of clinically significant prostate cancers and reduce unnecessary biopsies and treatment for benign and subclinical diseases. And the software for PIRATS has already been cleared by FDA and been widely used in clinical practices. And in general, standard development and recognition is a long process. And the usage of the advanced data analytics and the imaging capacities is still a fast-moving or fast-booming area. And I believe NIH and FDA will work together to develop or codify standards in this area to improve public health, just like they have been doing in COVID response and even earlier phases. One ongoing example is the metric I mentioned earlier, which actually sequestering some of the data for independent, standardized, and bias-free validation and testing for new software or data analytics in this area that can support translation and regulatory approval of the clinical use of such technology, which will impact the public health worldwide.
Absolutely, and it sounds like a really productive and, as you mentioned, evolving partnership. I want to get back a bit to the COVID question as well, because Dr. Justice, this is more of a question for you and your team, but if memory serves, when COVID-19 first broke out, there was a lot of, I think, demand and concern among our nation's most well-resourced research centers around essentially figuring out the nature of the disease, its transmission, its pathology. And I'm curious, how have these more recently developed advanced data capacities been used to better elucidate the nature and pathology of a novel virus like COVID?
Well, if you do a quick search through PubMed, you will see that there are probably at least 20 major papers that have come out of the VA addressing issues around COVID, whether you're looking at transmission, response to vaccination, all the current questions that people have, and now focusing on long COVID as well. Part of the thing that is very exciting about the VA is it's a health system that is a learning health system that has nested research within it. That includes investigators who both have expertise in statistical analysis and AI to some extent, and a great deal of expertise in clinical epidemiology and clinical research, as well as how that data is recorded. And bringing those people together, having them have worked on questions before, enabled us to much more rapidly address these questions in the present. In addition, we had already reached out and begun a very close collaboration with Department of Energy investigators using high-powered computing and their wonderful expertise on AI, and begun to develop that language so that, again, when COVID hit, we already had a collaboration that was well in place. All the, as I like to say, mother may I's had been approved. The data was there. We already knew each other. We already had started to work together. And that allowed us to move very rapidly to try to begin to respond to some of these questions. There are several publications that have both VA investigators and DOE investigators on them addressing very important questions in COVID. In one case, one by Dan Jacobson, which has been very, very highly cited.
Absolutely, and it sounds like creating those foundational partnerships really helped accelerate this pretty vital research out the gate. And on the subject of forward-looking medical research, I'm curious, Dr. Fricks, it looks like the National Artificial Intelligence Institute is going to be hosting one of its most substantial tech sprints early next year. And I'm wondering what topic or topics are you going to be addressing in the tech sprints, and what organizations, again, governmental, private sector, academic, are you planning on partnering for this particular sprint?
So as was, I think I alluded to before, this will be the third tech sprint that the National AI Institute has undertaken. And currently we haven't set a firm date about it because we have a lot of technical hurdles with what we're attempting to accomplish. But our vision is that in the next tech sprint, we will pursue an imaging technology for accelerating or improving the accuracy of reads of lung cancer scans that are routinely performed for either screening or diagnosing lung cancer in the veteran population. For a number of reasons, you know, lung cancer is such a heavy burden. It's a high mortality cancer that disproportionately affects our veteran population, for instance, and there are a number of mature technologies behind it. So our intent is that we would like to provision a safe environment computationally within the VA where we can invite outside collaborators to pitch solutions. Now, these would be more in line with like FDA approved, clinically ready solutions that we can evaluate then on VA data, on thoracic CT, chest imaging that is performed routinely during our care, to pick the, you know, best performing technology for use at the Department of Veterans Affairs. So there are a number of different, you know, technical challenges to pulling this off. Is that we have to pull together our images, we have to go through a de-identification phase to make sure that the data privacy is secure. But in general, we'll be offering this using the VA Enterprise Cloud resources. So we're working with a couple different departments, the Innovation Unit, the Enterprise Cloud people, to provision an environment that is computationally resourced for running imaging algorithms on our own images. So the idea then is we can have a true evaluation of how they would perform with the veteran population, which has some nuances that may not have been represented in previous data sets. And our goal is that the technology that we discover through this phase will give us a appreciation of where it could be deployed, and we have a few use cases in mind then. that's the goal that we intend to announce sometime next year. I would say for information on future tech sprints, our AI VA community, our newsletter tends to be the best first channel to hear about these plans when they're available.
Absolutely. And I want to turn back to a question for you, David, because you'd alluded to the structural usage of artificial intelligence, especially within a lot of DOE's core work. And it looks like AI and machine learning capacities have shown a good amount of promise for addressing large scale, I guess you could say, practical questions around infrastructure management. And I'm curious, how has DOE been using these capacities to better strengthen America's essential infrastructure, such as, say, energy grids and transit systems?
That's a great question. Thanks for asking. I think part of the potential here gets back to the structure of the problem. Much of the science research that was done previously started with a series of equations that were evaluated on supercomputers. That is very difficult in the range of infrastructure because you often don't have these nice closed form models, and yet you have lots and lots of data. You have data about how traffic systems are run, how how people use electricity off the grid. And I would add something like the manufacturing infrastructure, or of great interest now, the supply chain infrastructure to your question. So what you're faced with is a situation where you have lots and lots of data, and you don't have a closed form model, and you can see a lot of very, very complex behaviors. Now, what AI does is take an abstract model form and try to fit it to the data. It's very good at identifying correlations, but then that does leave you the question of what the causation is or not. But what this gives you the ability to do is to look at these complex systems, to predict behaviors based on what you've seen in the past, and then to design new systems. You can look at the resilience and the robustness of the electrical grid, of the transportation infrastructure in ways that we haven't been able to do before. Now, the other thing that AI really opens up is the ability to look at what we'll call the system scale. A lot of companies, organizations, cities, governments, and things like this have the ability to look very, very effectively at a local optimization. I can manage my own fleet, I can control my own traffic lights and things like this, but at the scale of AI and with the computational power that we have today, we can really look at the full system. We can look at the impact of the Port of Long Beach on the manufacturing supply chain, on fleet management for some of the large companies in the United States and things like this in ways that no single entity has the ability to do. That will require a lot of sharing data, figuring out how to respect privacy, how to respect intellectual property, and competitive advantage that companies spend many years developing through their data, and yet somehow enable the success and the optimization, robustness, and resilience, especially, of the entire system. We have seen in many cases, in response to, say, disasters, how a local optimization, one entity that's really optimized for their production of energy or something like this, is faced with a cold snap, a heat wave, a flood, a hurricane, or something like this. And because they have optimized it so tightly, and because they haven't thought about that integration with the rest of the system, they become a point of failure, whether it's a pipeline system or an energy distribution system. So the ability for the government to really facilitate a system-wide look at this using the tools of AI, the ability to process large amounts of data in a predictive fashion is a huge potential for AI.
Absolutely, and that concept of localized analysis fitting into part of a larger systemic view, I think is really interesting. And you alluded to questions of, for example, natural disaster response and resiliency as part of a larger system. And in looking at, again, the increasingly disruptive weather incidents and natural disasters that have really taxed America's infrastructure over the past decade, it looks like there's a really clear need for capacities that better, let's say, anticipate and get ahead of future stressors, kind of, in a way, predict and help get around the strain. And I'm wondering, how might, say, AI and machine learning be used to kind of look forward and address or maybe preemptively prepare for possible systemic strains?
Okay. Another good question, and let me start the answer here with a bit of a caution, and that is an AI can only learn from data and situations that it's already seen. And so if we are looking at natural disasters, weather patterns that we have not seen in the past, that limits our predictivity because we haven't seen it before. So we're training on existing data. What this does is really bring out the need to integrate our traditional modeling and simulation with AI. We do have predictive models. They're very computationally expensive. We'll need the exascale, the 10 exascale machine to evaluate that. We don't have the ability to really deal with scales very well. Local weather hydrology with more national scale in in an integrated fashion. So an AI, once we have seen the weather pattern, once we have generated synthetic data or predictions using traditional modeling and simulation, AI is very, very effective at speeding that up to cross scales. And once we can speed it up, it becomes very effective to use in decision making and things like this. And so bringing those two parts of science together, traditional modeling and simulation along with AI, gives us the ability to look, I think, into the future and really think about our response to disasters and things like this. And that might just be, how do we evacuate something? How does the electric grid recover? So thinking in terms of robustness and resilience. And we really can't ignore the problem of cybersecurity here, as we rely more and more, whether it's in the grid or the transportation, on the need to communicate between the vehicles, between the grid. We're going to have to make sure that not only can we detect intrusions and attacks, that we can have a system that is resilient and robust to those attacks. And so we have to think about those as well as the natural disasters.
Definitely. It sounds like the application to all forms of resiliency, whether, cyber or physical, are pretty immense. And I also liked your point, too, about how, you could only create AI models off of events or data that has already been studied or that has already happened. And I want to kind of backtrack a bit. Dr. Justice, you'd mentioned that VA had really done a lot of foundational work in establishing research partnerships, especially during the early stages of COVID, to respond to, again, what was a novel virus and a public health crisis that I don't think we'd seen in maybe about a century. And I'm wondering, in light of those already established partnerships and institutions, how might they be used, or how might they increase the efficacy of, let's say, studying the pathology of future viruses or future conditions, even if it's something as rudimentary as an evolution in an existing virus like COVID-19?
So I think there are a number of very important lessons. One of the things that I would also like to mention that in terms of helping prepare us to respond to COVID was the Million Veteran Program, which is nested within the VA, has already enrolled 850,000 veterans who've agreed to both give genetic material, have given it, and let us use their electronic records completely. The goal for that study is to have 2 million veterans, and they are continuing to enroll. Because we also had that genetic information, we were also able to look at COVID associations with genetics in terms of predisposition to infection. I think the biggest message actually goes well beyond AI, and that is that the federal government agencies need to get together and find ways to share data that are in compliance with all the issues that have already been raised by the other speakers, but is in near real time and appropriately linked so that we can understand, okay, a veteran is seen in the VA, then they're seen by Medicare outside of the VA at another institution. That's the same person. They are having outcomes that are both being documented in the VA and documented outside of the VA, for example, or the Centers for Disease Control data, which is controlled by the states. So there are a number of mother may I's that really have to get in place before we can bring these data sets together and really have an understanding of what the individual's experience is of an infection or any other health risk. We need to do that ahead of time, because to try to do that in the middle of an epidemic gets to be very, very difficult. I was involved in many, many phone calls and Zoom calls and meetings and more meetings to try to get data sets brought together. But because the VA had already put the data in Oak Ridge, had already worked out how to share that data, that was really the only data that was analyzed. In the future, we really need to bring in the Centers for Disease Control data and the Medicare data and the CMS data and other sources like Department of Defense, because then we would have a really complete sample and be able to understand the epidemic in near real time and address it.
Yeah, it sounds like this consilience is vital, because it sounds like one of the running themes here we're talking about is that your research and quality of your models is only as good as your data.
Absolutely.
Yeah, and if you remove, those limitations and really bring together, the expertise and obviously the information that other agencies have, or even other departments within your agencies have, that corresponds clearly to a greater quality and efficacy of research. That kind of brings me to my next question. It's a bit of an inner VA question, of course, and this is for Dr. Fricks. And NIA is, again, a relatively recently established institution, but has clearly done a lot of work in building in-house AI expertise between, for example, you, Dr. Fricks, and Dr. Alturovitz. And in light of NIA's leading role in VA's AI development and building that expertise, I'm curious, how has NIA helped collaborate with other departments within VA to contribute your expertise towards their research projects or even helping modernize their business lines?
Well, a good example of that is, as I mentioned before, there are a number of projects we've identified through the AI Tech Sprint that have gone on to various stages of piloting within the VA. And so I'll say this up front, that I'm not a clinically trained psychologist. I'm not a person to talk to about these sorts of, concerns that we have, but mental health is a top priority for the Department of Veterans Affairs. And it's public knowledge that veterans suffer a disproportionate number of, the risk of suicide is disproportionately high in the veteran population. So a number of the projects that we've pushed forward apply AI to see if we can do something to either improve our response to catch those veterans before it's too late, or to detect suicidal ideation, or perhaps just even mental health decline before it becomes a significant issue. So the two projects specifically that came from this most recent tech sprint are we will be applying natural language processing to better screen some messages that are received by the VA from veteran callers to determine if that person may, for instance, require additional screening, or guide them towards counseling, or if there's signs of distress in that message. Another project that was actually the top awarded project at this AI Tech Sprint is with a startup called Behavidence, where we're looking to pilot and test the efficacy of a system that veterans would opt into on their mobile devices, and it would track sort of metadata about their device usage. So how often are they looking at just very generic things like social media, or shopping, or games, or whatever it may be. Veterans would opt into the system, and based on the behavior categorized by their pattern of smart device usage, it would start to indicate whether or not this person is doing fine, or if their patterns have changed, or if they may need some additional they may be in distress because their pattern of behavior lines up with somebody who may be having some issues. And so we have a number of mental health initiatives, and we partner with the Office of Mental Health and Suicide Prevention at the VA here. We're also working with OMH to craft the Suicide Prevention Grand Challenge that we hope to have underway this next year, which would be another data competition similar to a tech sprint. And we're hoping that these AI tools will allow us to improve our capacity to screen for these issues and to catch them early, to catch them, before there's any sort of significant issue.
Absolutely. And it sounds like a really critical application of AI, because you're applying these to essentially what are models of behavior that are oftentimes very complicated and full of, potential indicators or risk factors that require a kind of sensitive and refined form of analysis. And we are unfortunately pretty close to wrapping up our time here, but I want to close up with a final question for you, Chi. And on the subject of diagnostics and of using AI to really improve, again, diagnostics and kind of patient outcomes, I'm wondering from your end, and in your experience at NIH, what have you found, or do you think are some of the areas of patient diagnostics that have shown the greatest promise to be advanced by the application of, say, advanced data analysis or information modeling capacities too?
Yeah, that's a billion-dollar question, and I don't think I'm in a position to really give any highlights on greatest promises. But in addition to what I already mentioned, and also Dr. Fricks just alluded to, I think in the area that can offer great opportunity is the point of care and digital health, especially for those aim for at home or real-time long-term continuous monitoring. And the response to pandemic highlight the importance of such technologies. And also this technology may enable us and open up a new way to managing or diagnosing chronic disease, which is currently a big burden to the healthcare system.
Absolutely, and sounds like it also has a lot of promise to help really elucidate the nature of something, for example, like long COVID, which is clearly something that obviously your office has focused a lot on as well, Dr. Justice. So again, I just want to thank you all so much for coming onto our program. Again, Dr. Justice, Chi, David, Dr. Fricks, really appreciate your insights, and thank you so much for joining us.
Thank you.
Thank you.
Thank you.
Thank you.